Okay, so good morning, students. So you must have gone. Hope that you must have gone through the previous videos. Okay, about boiling numerical. Okay, so today we'll be taking another different type of numerical. So we'll be continuing the discussion, and we'll be taking another different type of numerical. Okay, to compute the boiler performance from some more different parameters, okay, in a different way. Okay. So here, okay, so right, different the question is that in the previous case, in the previous question which was there, okay, so we were given the duration of the trial which was there, okay. So in one question it was given, in terms of kg per hour, okay. So this time what is given is that the duration of the trial which is there, the duration of the trial is given directly as 1 hour which is there. Okay, my duration of trial it is given directly as 1 hour. Okay, so whatever the values that are given here, okay, so all the values which are given here, they are for considering a 1 hour duration. Okay, so now the steam generated which is there, that is 35500 35,500 kg, and so that much will be for this in the 1 hour duration. Then that steam generated, it is at a pressure of 12 bar. Then the steam which is there, okay, so in the past questions that we had discussed, okay, so we were not given what the steam temperature. Okay, so here I know what is my temperature of steam which is there. Okay, so here I am know the mass of steam it is there. Then I know the condition of the steam. I know the temperature of the steam. Okay, then now in the this question, okay, so what is different in this question is that I have an economizer here. The temperature of water which is entering the economizer, it is 17 degrees Celsius, and the temperature of water leaving the economizer, it is 77 degrees Celsius. That means from the hot flue gases which are leaving from my boiler, okay, so they are passed to my economizer, and in the economizer the temperature of the feed water, that is raised by 77 minus 17. So the temperature of the feed water which is there, that is raised by 60 degrees Celsius by effect using the hot flue gases. So the hot flue gases, where do they come from? I am burning oil which is there. Okay, so I am burning oil, and in the one duration of the trial which was there, so I am completely burned 3,460 kilograms. That means around 3.46 tons of oil which is there I have burned, and the oil that I am burning, okay, so that is having a calorific value of 39,500 kilojoule per kilogram. So as I want you to, okay, recollect that when we had discussed about steam, about coal which was there, the calorific value of coal, it was approximately somewhere in the range of 27,000 to 28,000 kilojoule per kilogram is there. So oil which is there, that is definitely going to, since it is liquid fluid fuel which is there, so it is going to be having a higher calorific. The oil that I am using here, that is having a higher calorific value. Okay. So from the given data which is there, what I am supposed to calculate, I am supposed to find out what is my equivalent evaporation, okay, per kg of fuel. Then I am supposed to find out the thermal efficiency of the plant, and I am supposed to find out the percentage heat energy of the fuel, okay, energy which is utilized in the economizer. So now a major, see, at this 60 degrees, so how much is the heat percentage which is there, that is utilized for obtaining the 60% degree centigrade rise in the water temperature. Okay, so that is what is intended in the third part. So first part we know already how to arrive with that. Okay, so the second part also we know the expression. Now this question, okay, so we'll be seeing that, okay, in the third part how do I do that. Okay, so let us first start with the given data which is there. Okay, so firstly I am given the mass of steam which is there. Okay, so that is 35,500 kg. Then the condition of the steam which is there, that is it is having a pressure of 12 bar, and the temperature of the steam which is there, that is 250 degrees Celsius. Okay, then the temperature of the water which is entering the economizer which is there. Okay, so for that, since here, okay, so we have an economizer here. Okay, so what I am doing is that I am adding a new notation here. Okay, so TEI, so T, what is TEI denoting is temperature of water at the economizer inlet. Okay, temperature economizer inlet, TEI 17 degrees Celsius. So same ways I have TEO, temperature economizer outlet, that is 77 degrees Celsius. Then I have the mass of the fuel burnt and its calorific value. So I have mass of fuel. Okay, so the mass of fuel it is 3460 kg, and the calorific value of the fuel which is that is 39,500 kilojoule per kilogram. So my given data is here. Okay. So firstly, I am not told anything about the condition of steam here. Okay, I am just given the steam pressure and the steam temperature. Okay, so firstly, what I'll be doing? Let me have a look at my steam tables which are there. Okay, so in the steam tables, when I'm looking at the constant at the pressure tables which are there at the pressure tables, so for 12 bar which is there. Okay, so at 12 bar. From steam tables at a pressure of 12 bar which is there, my saturation temperature Tsat which is there, that is showing it as 188 degrees Celsius. Okay, so now this my saturation temperature for 12 bar it is 188 degrees Celsius, and my steam temperature actually that is 250 degrees Celsius. So now 250 which is that is obviously that is greater than 188 as we all know. So what is the condition of the steam here? And the condition of the steam which is here, it is superheated steam. Okay, the condition of the steam here that is superheated steam. Now what I can do is that from the superheated in the temperature from the enthalpy values for superheated steam. Okay, so firstly at the pressure of 12 bar and then for a temperature of 250 degrees Celsius. Okay, so I can find out the specific enthalpy of steam at 250 degrees Celsius, and the enthalpy of steam at 250 degrees Celsius which is there I am getting it as 2935.4 kilojoule per kilogram. Okay, so this value is there from the superheated from the specific enthalpy of superheated steam. Okay, so that I can get in page number 19 of the steam tables. Okay, if you are using the steam tables by R.S. Kurmi. Okay. No, I have the which is there, so I have found out what is my enthalpy of the steam which is there. Okay, so now I'll be requiring what is the enthalpy which is there before to find out the efficiency and all. Okay, and to find out the equivalent evaporation, all the parameters to I'll find out. Okay, so I'll be requiring the economy. I'll be requiring what is my feed water. Okay, so now firstly. Firstly, to start off with, okay, so what I am doing is that, okay, so let me find out the enthalpy of the feed water before it is entering at the enthalpy. Okay, so firstly, the enthalpy of the feed water, okay, at inlet of economizer. No, as always, as we had seen in the previous numericals, okay. So at the wherever the feed water inlet which is there, which was there, okay. So there we had given the notation as HF1. Okay. So the enthalpy of feed water at inlet that will be CPW into TEI minus 0. So that will be CPW is 4.187 multiplied by temperature at the inlet of the economizer. We had it was given as 17 degrees Celsius. Okay, so 17 minus 0, I'm getting it as 71.179 kilojoule per kilogram. Then next part which is there, okay. So this water which is there had a temperature of 17 degrees that is entering my economizer, and it is leaving the economizer at 77 degrees Celsius. So the portion of heat which is there, okay, portion of the heat or oblique the enthalpy added to feed water, it's a single term, right? Feed water, it's a single term. the economizer. Okay, so the portion of the heat or the water, how much is my enthalpy that is added to the feed water in the economizer. Okay, so that I am denoting as HE. Okay, so HE, E notation for economizer, H for specific enthalpy which is there. So HE equal to CPW into TEO minus TEI, right? The CPW, the notation for specific enthalpy of water. Okay, because we know that at the end, at the inlet and the exit of the economizer, the condition which is there, that is water, it is at existing as water only, it is not converting into steam. Then at the economizer outlet and economizer inlet. So HE which is there, okay. So I am getting as 4.187 into 77 minus 17, or implies the enthalpy which is added in the economizer I am getting as 251.22 kilojoule per kilogram. Next I have to find out the evaporation rate. This is my evaporation rate, Ma equal to the mass of steam upon mass of fuel. Okay, so my mass of steam was 35,500, right? 35,35500 kilogram divided by the mass of fuel oil with that was 3460 kgs. Okay, so my evaporation rate which is that I am getting as 10.26 kg of steam per kg of coal. Okay, so this part I'll be requiring enthalpy of the enthalpy added in the economizer, that also I'll be requiring, and the evaporation rate also I'll be requiring. Okay, now what I can do right now is that, okay, so now I can proceed to equivalent evaporation. Firstly, now when I'm discussing about the term of equivalent evaporation, okay, so there I am discussing just only about the boiler, right? The equivalent evaporation which is there. Okay, so because my phase change process which is there, that is happening only in my boiler. So how much is my what is the equation? Ma into, my standard equation was Ma into H minus HF1 upon 2257. This was my standard expression. But right now my feed water which is there, okay, so my feed water, it is also entering the economizer before it is proceeding to the, before it is entering the boiler. So implies, okay, so there is a small addition in this expression, Ma into H1 minus He minus Hf1, okay, upon 2257. So this will be my expression for the equivalent evaporation for this particular case. Okay. Now suppose I have the superheater also. Okay. So if I have the superheater also, but still the equivalent evaporation, it is considered only for the case of when I am considering my boiler. Okay. So equivalent, I am talking about equivalent evaporation for the boiler entity only. Okay. So my ME which is there. Okay. So that will be equivalent evaporation, that will be MA, I just found one. Okay, so 10.26 into H1 which is there, I had found out H1 2935.4, so 2935.4 minus HE 251.22 minus 71.179 divided by 2257. So the expression for equivalent evaporation which is there, those I am getting as 11.7878 kg of steam per kg of coal. So with this, my first part of the problem which was there, okay, so that first part it is over. Now I have to find out the thermal efficiency and the percentage of the energy, heat energy which is there, that is utilized by the economizer. Okay, so I am supposed to find out those two parts also. So now this next part which is there, to find out the thermal efficiency. Now, when I want to find out the thermal efficiency, now this in this case, okay, let me to go back to the question. So here I am asked to find out the thermal efficiency of the plant. Okay. So now what first I'll have to do is that, okay. So here we'll be seeing two cases here. Okay. So firstly, when I am considering only the boiler. Okay. And firstly, I'll be considering only the boiler. Then we'll consider the boiler and the economizer both. Okay. So we'll be taking both the cases and we'll be looking at the value. What are the values I am getting for both the cases. Okay. So thermal efficiency which is there here I am supposed to find out okay of the plant. So my efficiency of the overall so here basically I'll have to look for the overall efficiency which is there. Okay. So efficiency overall equal to MA into H1 minus HF1 divided by the calorific value. Why I am taking HF1 directly? Because I have to consider the enthalpy added in the boiler and the enthalpy added in the economizer. The initial condition before it is entering the boiler. Okay, so that means the feed water condition and the condition of the superheated steam which is there. So that's why enthalpy of the condition of the feed water given by HF1, specific enthalpy of feed water at inlet to the economizer, and H1 the specific enthalpy of superheated steam at the boiler exit. Okay, so that is why MA into H1 minus HF1 upon CV. Now MA I have found out already 10.26 multiplied by H1 which was there. Okay, so H1 I had already found out. We had taken the value of H1 from the tables, 2935.4 kilojoule per kilogram Kelvin. And the enthalpy of the feed water at inlet we had found out. Okay, in the previous slide, in the previous here, okay, page we had seen. Okay, so it was 71.179 and the 71.179, and then I am dividing it completely by the calorific value of the fuel which was there, and the calorific value of fuel was given as 39500 kilojoule per kilogram. So implies when I am calculating it, is when I am calculating it, I am getting it as 74.397 percentage. Okay, so because at the end I'll also have to multiply it by 100 to convert it into percentage. Okay, so my overall efficiency of the plant which is there, I am getting a 74.397 percentage. Now thirdly, I am supposed to find out the percentage of heat which is there, heat energy which is utilized in the economizer. So to find out the percentage of heat energy which is utilized in the economizer, it will be a small actually variation of the expression. Okay, it will be a small variation of the overall efficiency expression itself. Okay, so that will be that I can write it as percentage of heat energy is that I can write as MA into HE. Okay, so why? Because when I'm found out He, I have already taken only the enthalpy rise which is there in the economizer. I have not considered the enthalpy at the inlet to the economizer. I have considered the enthalpy rise only in the economizer. Okay, so Ma into He upon the calorific value. Just just a small deviation from this expression. Okay, so this which is there. Okay, so that will be let me also I can also maybe write it as efficiency of economizer. Okay, so the efficiency in the economizer which is there, that will be MA, it is 10.26 multiplied by the entire enthalpy added in the feed water in the economizer, that is 251.22 kilojoule. Okay, so 251.22 upon the calorific value, it is 39500. In this value multiplied by 100 and in percentage. Okay, so this when I'm doing, I'll be getting it somewhere in the range less than, it should be like less than 10 percentage. Okay, so I'm getting it as 6.525 percentage. So because of the use of the economizer which is there, okay. So if at all, if let me if, here if I am actually looking at speculating at a value, okay. So without the use of the economizer, what would have been the boiler? Okay. So without economizer, in this condition, okay. So what would have been my boiler efficiency, my plant efficiency? Okay. So that I can what I can do 74.397 minus 6.525. Okay, so that value what I am getting it as 67.873 percentage which is there. Okay, so this would have been the efficiency which is there. Okay, without the economizer. So because in this plant I am using the economizer, so I have an efficiency overall efficiency increase of 6 percentage. So 6.25 percentage. Okay, less amount of flue gases are less amount of energy it is wasted in the form of flue in to the flue gases. Okay, so what was so we'll go through quickly go through the entire actually. Firstly, I'm given the duration of the trial which is there as 1 hour. Then the steam generation, all the values we are given for 1 hour, and I'm supposed to find out equivalent evaporation, the thermal efficiency of the plant, and the percentage heat energy of the fuel utilized by economizer. So from the steam tables which are there, okay. So when I look first check for 12 bar, what was the saturation temperature? It was 188 degrees Celsius, and my steam temperature is 250 degrees Celsius. So already my steam which is that is in superheated condition. So next what I do is that to find out the enthalpy of superheated steam, I'll be referring directly to specific enthalpy of superheated steam, and I'm at 250 degrees Celsius which other I'm getting the value as enthalpy of steam as 2935.4 kilojoule per kilogram. So once I'm getting the enthalpy of the superheated steam, next at the inlet of the economizer which is how much was my enthalpy, I found out the enthalpy of the feed water inlet feed water at inlet of economizer. Then how much was the fraction or how much is the fraction of heat that is added in the economizer, okay, from the economizer before it is entering the boiler. So that what I have found out as He. Next, I am also finding out the evaporation rate, which is the so evaporation rate I have obtained as 10.26 kg of steam per kg of coal. Then using these values, okay, so I am finding out the equivalent evaporation of the boiler. Okay, so I want to make it specific. I am I am considering only the boiler here. Okay, so equivalent evaporation of the boiler which is there. So that is why I have subtracted the what was the enthalpy added in the feed water in the economizer and the at the enthalpy of the feed water at the inlet of the economizer both. Okay, so only then I'll be having how much is the heat added in the just in the boiler. Okay, so accordingly I'm getting my equivalent evaporation as 11.878 kg of steam per kg of coal. Then we are going to the thermal efficiency, and here since I have been asked to find out the thermal efficiency of the plant, okay, so I have to consider the boiler, the economizer both. Now if at all in my plant which was there, okay, so I was also given the values, the term superheater. Okay, so if I was given the term of superheater, so then here I would have been considering the enthalpy added in the superheater also. Okay, so I would have, so overall means enthalpy of the enthalpy, so He plus H boiler plus H superheater. So all the three terms which are there we'll have to consider. Okay, if I am given the superheater, okay, then to find out, then we found out the percentage of heat energy which was utilized in the economizer. Okay, so for that we considered only the energy which was enthalpy which was added in the economizer, which was 251.22 kilojoule per kilogram, and I have got the efficiency or the percentage of heat energy which was utilized in the economizer as 6.525 percentage. Okay, so with this we'll be coming to the we will conclude this problem. Okay, so thank you for watching, and keep the channel like, okay, so keep watching for more videos.